Hello all. Today we will see open circuit and short circuit test on the transformer. The objective to perform this test on the transformer is to find out the equivalent circuit parameters of the transformer, to find out voltage regulation of transformer, and to find out efficiency of the transformer. So without loading the transformer, we can find out the efficiency and regulation of the transformer. We can do this test in other way by directly loading the transformer. But if the transformer rating is too high, it is impossible to load the transformer because it is an inefficient way. Lot of energy is wasted in the form of heat. So the big transformers, to find out the efficiency and regulation, we can perform the open circuit and short circuit test, because here we can find out the efficiency and regulation by indirect way. So let's first see the open circuit test on the transformer. So this test is performed by applying the rated voltage to one of the winding, keeping the other winding open. So generally the open circuit test is performed on the LV side and HV side by keeping HV side open. The reason behind this is, if we perform the open circuit test on the HV side, the no load current on the transformer is very small and the voltage is inconveniently high. So we need to connect such high range meters, which is not convenient. So if we perform the open circuit test on the LV side, the current is in the measurable form and also the voltage range is also small. So it is recommended to perform the open circuit test on the LV side of the transformer. So V0 is equal to the secondary voltage of the transformer. Whatever wattmeter reading shows, it is indicated as W0 and it is the input power given to the transformer. So in the open circuit test, we are not connecting any load on the transformer, so output is 0. So whatever power is measured by the transformer, it is used to supply the iron losses and the copper losses at no load. So no load current of the transformer is so small as compared to the full load current, so we are neglecting the copper losses. Hence whatever wattmeter reading shows, those are nothing but the iron losses or copper losses, or iron losses or core losses. So that core losses help us to find out the no load branch or shunt branch equivalent circuit parameters. So core loss is equal to V0 I0 cos phi 0. So with the help of this formula, we can find out the power factor of the transformer cos phi 0. With the help of that, we can find out the active component of the current IW, which is nothing but I0 cos phi 0, and magnetizing component of the current I mu, which is I0 sin phi 0. Now the R0 is nothing but the V0 upon IW and X0 is nothing but the V0 upon I mu. So with the open circuit test, we can find out the iron losses or core losses, as well as we can find out the equivalent circuit no load branch parameters, active component of the current IW, magnetizing component of the current I mu, and we can find out the R0 and X0 with the help of open circuit test. Now next test is the short circuit test. Now short circuit test is always conducted on the HV side. Now if we conduct this test on the LV side, voltage will be inconveniently small and current will be large. So it is recommended to conduct the short circuit test on the HV side. So very small voltage is required to circulate the rated current from the LV winding. So very small voltage VSC is required to circulate the short circuit current. So that's why very small flux is produced. So that's why we are neglecting the core losses. They are very small, so we neglect the core losses during the short circuit test. So whatever power is dissipated in the form of heat, that is recorded by the wattmeter, and those are nothing but the copper losses. So WSC is ISC square R01. With the help of this formula we can get R01. Z01 is nothing but VSC upon ISC, and with the help of Z01 formula we can find out the X01. So short circuit test help us to find out equivalent resistance on the primary side, equivalent reactance on the primary side, and equivalent impedance on the primary side. Efficiency of the transformer. Now formula of the efficiency of the transformer is nothing but the output upon input. So we know the KVA rating of the transformer. So KVA rating for any given power factor we can find out, and for any loading condition we can find out the efficiency of the transformer. So if X is the percentage loading of the transformer, then formula for efficiency is X into KVA rating into cos phi divided by X into KVA rating into cos phi plus iron losses plus X square copper losses. So if the loading of the transformer is vary in the percentage of X, if you see the copper losses vary in terms of X square. Now regulation of the transformer. If the input voltage is held constant, the voltage at the secondary terminal varies with the load. So regulation is defined as change in the magnitude of secondary voltage when the load is thrown off with the primary voltage held constant. In this case, the expression for regulation is given by percentage regulation is I1 R01 cos phi 1 plus minus I1 X01 sin phi 1 divided by V1. So here I1 is calculated by the formula KVA is equal to V1 I1 into 1000, and plus sign is used for lagging power factor and minus sign is used for leading power factor. It is observed that regulation is very good at unity power factor. Value of the regulation must be in the limit of plus minus 5%. If the regulation is less, it means that transformer is good. So regulation is negative at leading power factor and regulation is positive at lagging power factor. So thank you very much.